morning, one and all. Myself, Sreevani, working as an assistant professor in the Department of Electronics and Communication Engineering in Inst of Aeronautical Engineering, Dundigal, Hyderabad. So, in the today's lecture, we are going to learn about oblique incidence with perpendicular polarization. So, what do you mean by oblique incidence? How it is related to the perpendicular polarization? We are going to learn in this particular lecture. So why we are going to learn about this oblique incidence with perpendicular polarization means, before going to learn about that oblique incidence with perpendicular polarization, it is also called as horizontal polarization. Let it be first Snell's law of refraction and critical angle calculations are independent of type of the polarizations. As we know that types of incidences we have discussed in the previous lectures, types of incidence first. There are two cases of incidences are there. One is normal incidence and the next one is oblique incidence. Under normal incidence case, we have analyzed two cases as normal incidence with a plane dielectric boundary as well as normal incidence at a plane conducting boundary. In the normal incidence at a plane dielectric boundary case, we have considered one interface, and below this interface we have one medium, let it be medium 1, and in the above this interface we have medium 2, and these two mediums are, let it be, sometimes homogeneous types and sometimes isotropic type. If those two are homogeneous type, means both the mediums are, we have considered here, both are dielectric medium. Isotropic type, one is considered to be conducting medium and other will be like dielectric medium. So depending upon this, we have analyzed normal incidence at a plane dielectric boundary. There we have got two relations, one is tau and one more is gamma. Where tau is said to be transmission coefficient, it is the ratio of transmitted wave field strength to the incident wave field strength, and reflection coefficient as gamma, and which gives us, it is the ratio of reflected wave field strength to the incident wave field strength, right? So now in this case also, coming to the oblique incidence, here also we have two cases, oblique incidence with a dielectric boundary and oblique incidence with a conducting boundary. So oblique incidence with a dielectric boundary case, in the previous lecture we have learned about Snell's law of reflection as well as Snell's law of refraction. As first law is called theta I is equal to theta r, this is called Snell's law of reflection, and sine theta t by sine theta I equal to beta 1 by beta 2 is called as one of the relation of Snell's law of refraction or transmission, right? So depending upon this one, we have got one of the angle called theta c, that is sine inverse of beta 2 by beta 1, right? So now that is Snell's law of refraction and a critical angle. What do you mean by critical angle? Means the angle at which total internal reflection will takes place is, the concept is called as critical angle, and it is represented with theta c. Generally we use the notation for angle is theta, and C stands for critical angle. So Snell's law of refraction and critical angle calculations are independent of the type of polarizations, right? So types of polarizations. Now coming to this one, in oblique incidence, to derive the formula for the transmission coefficient as tau and the reflection coefficient as gamma, then consider two special cases of the polarizations. Those two special cases are as, like, first case is horizontal or perpendicular polarization, and we are representing the two notations for transmission coefficient as tau and for reflection coefficient as gamma. Now transmission coefficient for the perpendicular polarization means we are representing it with tau perpendicular, and for the reflection coefficient we are representing with gamma perpendicular, where the perpendicular symbol resembles a type of polarization which we have used in that particular concept. Similarly, vertical polarization is also called as parallel polarization. And here the notations are tau parallel and gamma parallel. Generally, the two parallel lines are representing the parallel condition, and the tau and the gamma are the respectively called as transmission coefficient and reflection coefficient for the oblique incidence. Now, in detail, we are going to learn about first case as horizontal or perpendicular polarization, right? So now to learn about this perpendicular polarization or horizontal polarization, firstly, what do you mean by horizontal or perpendicular polarization? Now, how the which field we have considered, which plane we have considered, and in which direction the wave is to be propagating. Depending upon that, wave propagation vectors we are supposed to consider. From the wave propagation vectors, we'll be calculating this transmission coefficient and the reflection coefficient of the oblique incidence with perpendicular polarization or horizontal polarization. Okay. Then first definition of a perpendicular polarization or horizontal polarization. So it is defined as the perpendicular polarization is defined as it is the polarization in which the electric field of the wave is perpendicular to the plane of the incidence, right? So electric field, perpendicular polarization case, the electric field is perpendicular to the plane of incidence. Suppose if we are going to discuss about vertical or parallel type case, the magnetic field is perpendicular to that of plane of incidence. Now we are discussing horizontal or perpendicular polarization means it is defined as the polarization in which the electric field of the wave is perpendicular to the plane of the incidence. Now electric field vector is perpendicular to the xz plane. So which plane we have considered means xz plane. Horizontally, we are considering z plane, z direction and x direction. XZ plane means the direction means this plane is also called as XZ plane or y equal to 0 plane. Okay, XZ plane. So the direction, propagation direction we are going to consider with respect to this plane is y, AY, right? So XZ plane means y direction. Suppose if we are considering XY plane, means this XY plane is also called as Z direction plane. Or if you are going to consider YZ plane, means X direction we are supposed to consider, right? So electric field vector is perpendicular to the plane of incidence means that plane we have considered is XZ plane. Okay, hence it will have component along the y-axis, right? Suppose if we are considering XY plane, means the component will have on the we are considering xy plane, z axis, right? So like that, if depending upon the plane we have considered, the propagation direction will change, right? Then the electric field is transversal to the plane of incidence. Then they are also known as transverse electric waves. Transversal means perpendicular to the, right? So the electric field is perpendicular to the plane of incidence means transversal to the plane of incidence. Then these horizontal or perpendicular polarization wave is also called as transverse electric waves. In short, we'll call it as TE waves. TE, transverse electric waves. Okay, so horizontal or perpendicular polarization case that waves are said to be transverse electric wave in which we have considered XZ plane and the wave in which it is propagating is along the y direction. Okay, now here is the diagram. Now suppose when the incident wave is touches the boundary, means at z is equal to 0, we have an interface and below z equal to 0, medium 1 is exist, above z equal to 0, medium 2 exist. So for the characteristic parameters of medium 1 and medium 2 are respectively given by here mu1 epsilon 1, mu2 epsilon 2. Okay, and theta I stands for incident wave making angle and theta R is given for the reflected wave making angle. And the field strengths are given by here for the incident wave. This is called incident wave, and here it will be this one is reflected, and in the medium 2 we have got transmitted wave, right? So when the incident wave touches the boundary, when the incident wave strikes the boundary, part of this incident wave is reflected back to the same medium, part of this will be transmitted to the next medium. Hence, theta I, theta r, and theta t making angles of respectively incident wave, reflected wave, and transmitted wave. Right? As we know that EI and HI are the electric and magnetic field intensity vectors, and ER and HR are electric and magnetic fields intensity vectors for the reflected wave. Similarly, ET and HT are representing transmitted wave, electric as well as the magnetic field intensity vectors. And where KI, KR and KT represents propagation directions of these respective waves. Sometimes gamma is also used. In our case, we use here K. And gamma equal to K, these two are resembles propagation directions. Okay. So if these two are perpendicular, the propagation direction is also perpendicular to that of the rest of the fields E and H. Okay. Now depending upon this, we will draw here three propagation vectors of incident wave, reflected wave, and transmitted wave. So consider that uniform plane wave is incident obliquely with E perpendicular to the plane of incidence related to perpendicular polarization. Let us assume that incident wave propagates in the first quadrant of XZ plane without loss of generality. So first I am going to draw here incident wave propagation vector. So this is incident wave propagation vector, Z direction, X direction, and when the incident wave is moving in this particular direction, then this is called as gamma 1 I, right? So this is theta I, and gamma 1 cos theta I, and here it will be gamma 1 sin theta I. Okay, wave propagation vector for the incident wave, right? So if the x means initially we are assuming incident wave is propagates in the first quadrant of xz plane. So consider xz plane, first quadrant of xz plane means x value and z value both are representing two positive values. Okay, and consider another propagation vector that is for the reflected wave. Means when the reflected wave lies along the second quadrant of xz plane. This is z, this is x, and reflected wave, right? So this reflected wave is given by here 0, here is horizon, and minus gamma 1 cos theta r, and this is gamma 1 sin theta r. The angle is given by here theta r, and the propagation vector is represented with gamma 1 r. This is propagation vector, and here is the r. R stands for reflected wave. Okay, and similarly last one is for transmitted wave. As we know that the incident wave and transmitted wave directions are the same, hence here the transmitted wave is also aligned in the first quadrant of xz plane, z, x. Okay, 0. This is the propagation vector for transmitted wave, and this is the angle which is making by this transmitted wave, and from this gamma 2 cos theta t, and here it will be gamma 2 sin theta t. Okay, so these are the wave propagation vectors for incident, reflected, and transmitted waves, right? So for the first one, if you observe, the incident wave which is propagating in the first quadrant of xz plane means z and x components are positive, and if you observe the reflected wave, it will be aligned in the second quadrant of xz plane means x value is positive and z value is to be considered as negative. And similarly, the third one is for the transmitted wave, this propagation vector is aligned in the first quadrant of xz plane. Okay, So this is for incident wave propagation vector, and this is reflected wave propagation vector, and last one is transmitted wave propagation vector. Transmitted wave propagation vector. Depending upon these three, we are going to write the propagation vectors for the first, then we will substitute in the place of magnitude and the directions place, we will substitute gamma and z values. Then finally, we will simplify the equation for transmission coefficient and reflection coefficient of oblique incidence with perpendicular polarization. I think understood how we have drawn this wave propagation vectors for incident, reflected and transmitted waves. Okay, from these three we will draw here. Means let us assume that incident wave propagates in the first quadrant of xz plane without loss of generality. Then first means if you are writing the equation for electric field strength E, then it will be initially we are assuming the electric uniform plane wave is propagation characteristics case, where we have assumed electric field is always in the with respect to the x direction and the magnetic field is with respect to the y direction. The wave which is to be propagating in the opposite to that of 2 will be considered as z direction. Now, we are writing electric field intensity vector E with the magnitude and the phase directions. EI means E is the magnitude, let it be, I am representing it with E naught as a magnitude and E power minus gamma 1 into Z, where gamma 1 stands for medium 1, E1 or E01 like that. So for the medium 1, E1 is given by here, its magnitude is representing with E1, E power minus gamma 1 into Z, where gamma 1 is given by propagation vector in the medium 1 and Z is to be considered as propagation direction, right? So in order to simplify this one, suppose if you are going to write the equation for incident wave EI equal to EI into e power minus gamma 1 Z. Suppose if you want to go write the equation for reflected wave, then it is ER into e power minus gamma 1 into Z. And if you want to write the equation for transmitted wave, it will be ET equal to ET into e power minus gamma 2 into Z. Why? Because means the initially we are assuming the when the incident wave strikes the boundary, part of incident wave is reflected back to the same medium. Part of that incident wave is transmitted to the next medium. Means in the medium 1, if you observe clearly, there exists two waves. Those two are incident wave and reflected waves. That's why propagation constants are representing gamma 1 and gamma 1. Whereas in the medium 2, the transmitted wave, that is ET, only exists, hence we are representing its vector with gamma 2. Where gamma is the notation for propagation vector, right? So in order to simplify this one, gamma 1 into Z case, first we are writing from the propagation vectors, gamma 1 into I means power I, where I stands for incident wave. In order to identify that wave, incident wave, we are writing here the simple notation for that is I. Gamma 1 in power I into Z equal to. So from the propagation vector, how we are going to write the this gamma 1 means, see from the xz plane, first quadrant means incident wave is like this. So this is theta I, this is z direction, x direction. This is given by gamma 1 cos theta I, and let it be this is gamma 1 into sine theta I. Then this is propagation direction, let it be I. Okay. Now from this, how we are going to write this equation means gamma 1. Why? Because we are writing the equation for medium 1 propagation constant. That's why that is represented with gamma 1. Generally, propagation constant is represented with gamma, and for medium 1, we are writing it with gamma 1. Where I for incident wave. Okay. Now, from this propagation vector, first we are going to write the equation for gamma. So already always we are considering the real terms are always with respect to the z direction and the imaginaries are with respect to the vertical direction as like this. Why? Because this is representing real axis and this is representing imaginary axis. Okay, so based upon this, gamma can be written as gamma 1 cos theta I, in which direction it is propagating? Z direction. Hence, gamma 1 cos theta I az plus gamma 1 sin theta I into, in which direction it is moving? X direction. Hence, it is AX. Okay. So, gamma 1 cos theta I az plus gamma 1 sin theta I AX. This is nothing but total 1 is given by gamma 1. Okay, dot product with z. Z means z direction. Z component is expressed as here z az plus x ax. X z plane, no? So that's why z component is along the az and x component is along the ax. Okay, now dot product between these two will gives us, see, gamma 1 into z cos theta I means gamma 1 into cos theta I az into z az. Az dot az value is 1, then gamma 1 z cos theta I is left out. Then similarly, if you multiply this az with ax, its value is equal to 0. As we know that dot product representation of same unit vectors result is 1 and a dot product representation of adjacent or other vectors result is equal to 0. That's why we are multiplying this z with z, its value becomes 1. We are multiplying this z with x, its value is equal to 0. Then az dot ax equal to 0, then we need not consider gamma 1 x coefficient. Similarly, this gamma 1 sin theta I ax is multiplied with z az means it will be given by here gamma 1 x sin theta I. Ax dot ax value is 1. That's why gamma 1 x sin theta is left out. And if we are multiplying ax with az, its value becomes 0. That's why we have got here two components, gamma 1 z cos theta I plus gamma 1 x sin theta I. Suppose if you take gamma 1 as common between these two, then this can be written as gamma 1 into z cos theta I plus x sin theta I. This is nothing but gamma 1 into z only. Okay, but we have considered the electric field intensity vector for the medium 1 as E1 equal to E1 into e power minus gamma 1 into z. But we are writing the propagation vectors from the incident, reflected and transmitted waves. That's why we have considered the notation as EI, where I stands for incident wave. Okay, so for that incident wave, EI is equal to magnitude is EI and the propagation constant is e power minus gamma 1 into z, and that will be given by here from this relation. Means e power minus gamma 1 into z cos theta I plus x sin theta I into which direction? Y direction. Why? Because which plane we have considered? XZ plane. XZ plane means the propagation direction will be on Y direction. That's why AY. Okay. Then, now to simplify this one means based upon that propagation vector of incident wave, we have got here EI. Now similarly, if you observe in that first figure, there exists along with the incident wave of electric field intensity vector, there exists magnetic field intensity vector HI also. To write the equation for HI, we use the Maxwell's equation. What is this Maxwell's equation? Means from the Faraday's law. According to the Faraday's law, it is given by, that is del cross E bar equal to minus dou V bar by dou T. Okay, then for a time varying fields, the dou by dou T is replaced by j omega minus j omega and B is given by mu into h bar. B and h relation is given by B equal to mu into h. Then if we substitute B by mu into h, then it becomes del cross E bar equal to minus j omega mu into h bar. Right? So we are writing the equation for incident wave, hence del cross EI bar equal to minus j omega mu 1 into HI. 1 stands for the medium 1. Now from this, HI is equal to del cross EI by j omega mu 1 with a negative. Okay. Now, upon simplification of this del cross Ei by j omega mu1, we are going to get the equation for incident vector magnetic field intensity. Okay. To write that equation first. So, Hi is equal to what we have written? Hi equal to del cross Ei by minus j omega mu1. So first minus 1 by j omega mu1 is to be considered as a constant. Now we have expression this del cross Ei in the determinant form. So determinant form means matrix form. We are going to write the matrix form. There exist 3 rows and 3 columns. In the first row, we have written all the 3 unit vectors as Ax, Ay and Az. And in the second row, we have written all the partial derivative terms dou by dou x, dou by dou y and dou by dou z. And in the last case, del cross Ei. Previously, what we have written, that is vector Ei is given by here Ei into e power minus gamma 1 z cos theta I plus x sine theta I. Now, in place of that, we will consider this equation. So, Ei component, y component only exists. And the xz plane means x component is 0, z component is also 0. Only we have y component, that is given by e power minus gamma 1 into z cos theta I plus x sine theta I. Now, upon expanding this equation, we are going to get minus 1 by j omega mu1 into first. Ax into, first consider, if you consider the first component as Ax, first or first column can be neglected, and the determinant between these two, that between these two is given by dou y of 0 is 0 minus dou by dou z of this thing. E power minus gamma 1 into z cos theta I plus x sine theta I. Right? Then theta I, then minus ay into. If we consider the second component as ay, then ay, first row, second column we neglect, then the determinant fit between first and last components means dou by dou x of 0 is 0 minus dou by dou z of 0 is 0. Then plus third row means az into. So if you consider first row and third column means the determinant between these two will gives us az into first dou by dou x of e power minus gamma 1 into z cos theta I plus x sine theta I. Okay, that's fine. Okay, now upon simplification, this one and multiply this negative with internal function, then this becomes minus into minus plus and 1 by j omega mu1, and here ei component is also exist, right? So ei by j omega mu1 into dou by dou z of, if you simplify this one, e power minus gamma 1 into z cos theta I plus x sine theta I. E power x differentiation is e power x into x differentiation means e power minus gamma 1 into z cos theta I plus x sine theta I into, so x component, we are differentiating this one with respect to z means x can be treated to be a constant, then differentiation of constant becomes 0, hence we have got first component as minus gamma 1 cos theta I into what we have written here, ax, first direction, ax. Okay, then this thing, then, and if you multiply this negative with this term, then it becomes minus dou by dou x of this thing means here it will be e power minus gamma 1 into z cos theta I plus x sine theta I into differentiation of this one becomes as with respect to, here also x can be treated to be, z can be treated to be a constant, hence differentiation of constant becomes 0, and we are differentiating this one with respect to x, then it becomes minus gamma 1 sine theta I into a z. Okay, upon simplifying this equation, ei by j omega mu 1 into in between these two. Here gamma 1 and gamma 1 is common. Then gamma 1 into e power minus gamma 1 into z cos theta I plus x sin theta I is common between 2. Then we will simplify the rest. Means minus cos theta I ax minus cos theta I ax, and here negative is there, here negative is there, minus into minus becomes plus, then sin theta I into az. Okay, so this is the value is observed here. See, hi is equal to ei into gamma 1 by j omega mu 1 e power minus gamma 1 z cos theta I plus x sin theta I into minus cos theta I ax plus sin theta I into az. This is the way we have got the solution. Now from this, if you substitute, means gamma 1 by j omega mu 1 value is to be considered as intrinsic impedance eta. Why? Because as intrinsic impedance from the wave characteristics, intrinsic impedance eta formula is given by j omega mu 1 by gamma 1. Right? As we know that the general formula for this is j omega mu 1 by, if you write the equation for this gamma 1 as j omega mu 1 plus into sigma plus j omega epsilon 1, then root over. If you simplify this equation, j omega mu 1 by sigma plus j omega epsilon 1 root over. Right? So this is the way we have got the solution for this intrinsic impedance eta. So from this relation here, if you observe, this is the one which is given by, means j omega, this gamma 1 is there in the numerator, and if you take this into the denominator, then it becomes j omega mu 1 by gamma 1. What is this j omega mu 1 by gamma 1? Nothing but eta 1. That's why we replace this term by eta 1. Then hi is equal to ei by eta 1 e power minus gamma 1 into z cos theta I plus x sin theta I into minus cos theta I ax plus sin theta I az. Okay, so this is the way we have got the incident wave electric field intensity vector and magnetic field intensity vector as ei and hi. Okay, so similarly er, hr, et, ht are also to be evaluated. Okay, so now to evaluate those two, again, which propagation vector we need to consider for the reflected wave propagation vector. So as we know that reflected wave propagation vector is aligned in the second quadrant of xz plane, hence this will be the direction, and propagation direction is like this, and this is theta r, and here it will be gamma 1 cos theta r, and this is gamma 1 sin theta r, and second quadrant z value to be considered as negative. So from this reflected wave propagation vector, we are going to write again the same formula for er is equal to er into e power minus gamma 1 into z. To calculate this gamma 1 into z, we will write from this propagation vector, we are writing the equation as minus gamma 1 cos theta r az plus gamma 1 sin theta r ax. Why we have considered here negative? Why? Because if you observe, the directions of incident and reflected, two are moving in two opposite directions, and here we have considered second quadrant of xz plane, means z value to be considered as negative. That's why minus gamma 1 cos theta r az, gamma 1 sin theta r ax plus z vector z az plus x ax. This is common for three vectors as incident wave and reflected as well as transmitted. Okay. Now from that, again multiplication between these two, resultant will be minus gamma 1 z cos theta r plus gamma 1 x sin theta r. If you take gamma 1 as common, minus z cos theta r plus x sin theta r. So the previous equation is similar, but except in place of I, we have written here r, right? And er is equal to er into e power minus gamma 1 z, and this gamma 1 z value is to be written as this. And unit vector, as we know that xz plane means y direction, hence ay. Okay. Then to write the equation for HR, we are considering again the Maxwell's equation from the Faraday's law, that is del cross ER bar equal to minus j omega mu 1 HR bar. Why? Because what is the formula? Del cross E bar equal to minus dou B bar by dou T. So again for the time varying fields, this dou by dou T is replaced by j omega minus j omega, and B is given by mu into H, and for reflected it is written as minus j omega mu into HR. So this del cross E bar equal to minus j omega mu 1 into HR. Here also the reflected wave is also on the medium 1, hence we are writing all with respect to the 1 only. Okay. Now from this, to get the value of HR, now simplify this equation, then del cross ER bar by minus j omega mu 1. How we have evaluated in the case of incident wave, similar evaluation can be done for this reflected wave also. Okay. Now del cross ER bar equal to minus j omega 1 into HR. Now HR is equal to, as we will write the equation for this del cross ER bar, that is del cross ER bar equal to determinant form AX, AY, AZ as the first row, dou by dou X, dou by dou Y, and dou by dou Z as the second. And for the X component 0, Y component as ER into e power minus gamma 1 into minus Z cos theta R plus X sin theta R into AY. Means AY component is this and AZ becomes 0. Right? So if we evaluate this one upon expansion of this and after simplification, we will be getting the value for HR is ER by eta 1 e power minus gamma 1 into minus Z cos theta R plus X sin theta R into cos theta R AX plus sin theta R AZ. Okay. So here gamma 1 per R and gamma 1 I will have the same magnitude since both the waves are in the medium 1, and the directions in which they are propagating is changes, means opposite to each other. Okay. So from this ER and HR to be evaluated. Now next is to write transmitted wave field strength ET and HT. See, the transmitted fields will have a similar expression with the incident field, except that theta I is replaced by theta T and gamma 1 is replaced by gamma 1, gamma 2. Why? Because incident wave is moving in the field 1 and medium 1, whereas transmitted wave in the medium 2. Right? Then from that, we will be writing here the equation for ET as ET, means in general, ET equal to ET into e power minus gamma 2Z, 2 into Z. Gamma 2 means transmitted wave is in medium 2. That's why propagation vector, propagation constant for medium 2 is representing with gamma 2. So ET e power minus gamma 2 into this equation. Okay. So now from that, in order to write the HT equal to del cross ET by j omega mu 2. Right? Why? Because we are writing for the medium 2. Now HT equal to del cross ET by j omega mu 2, and upon simplifying this equation means as a determinant form and matrix form, 3 by 3 matrix form, if we evaluate, then HT will obtain as ET by eta 2 e power minus gamma 2 Z cos theta T plus X sin theta T into minus cos theta T AX plus sin theta T AZ. Okay. After simplifying all EI, HI, ER, HR and ET, HT, we will finalize all equations in one single table. See, we observe here, in the table 1 means region 1, there we have considered the region 1 to be lossless medium 1, lossless dielectric medium. Here also region 2, lossless dielectric medium. As we know that lossless means as propagation constant gamma is given by j omega mu into sigma plus j omega epsilon. If we consider the propagation constant as like this, for the lossless or perfect dielectric medium case, sigma is assumed to be 0. Then if we substitute sigma by 0 in this case, then gamma can be written as j omega mu into j omega epsilon root over. Then gamma can be written as j omega into root mu epsilon. Now from this, alpha equal to 0, beta can be considered as omega root over mu epsilon. Means for a lossless dielectric medium, we have got only phase constant, there is no real term. So for that, EI equal to EI into e power, previously what we have written, for losses there exists alpha. For lossless there is no alpha. That's why gamma 1 is replaced by j beta 1 and all beta 2s like this. So EI equal to EI into e power minus j beta 1 z cos theta I plus x sin theta I AI. Similarly for HI, then ER and HR. See, if you observe in the first quadrant, XZ plane, incident wave is exist in the first quadrant. That's why two values becomes positive, and reflected wave will be aligned in the second quadrant of XZ, means Z component as negative and X becomes positive. These two are ER and HR. Similarly, ET is also aligned in the first quadrant of XZ. That's why Z and X components to be positive only. Okay. Now keep in mind this, all 6 are important. Based upon this, we are going to derive reflection coefficient and transmission coefficient with the oblique incidence with perpendicular polarization. Okay. Now, based upon that table, the incident electric field intensity vector in medium 1 is given by here, EI equal to EI into this equation from the table. The incident magnetic field intensity vector in the medium 1 as HI, right? And the reflected electric and magnetic fields are ER and HR as like this. Now consider individually 1, 2, 3, 4 equations, right? Now from the transmitted fields, the ET and HD are given by like this. So continuously 1, 2, 3, 4, 5, 6 equations are EI, HI, ER, HR, ET, HD. Okay. Now from this we are going to derive reflection coefficient and transmission coefficient of this perpendicular polarization, right? So now to derive that, we use here boundary conditions. Which boundary conditions we are going to consider here means the interface is existing between two dielectric media, right? As we know that between two dielectric, the boundary conditions are given by E1t equal to E2t as one of this one. Means tangential components of both the mediums 1 and 2 of electric field strengths are same across the boundary or continuous across the boundary. Depending upon this, E1t equal to E2t. See, from the boundary conditions, the tangential components of E and H must be continuous at the interface where Z is equal to 0. Okay, consider all the 6 equations. In that, you just substitute Z by 0. Then what actually remaining? That equations we are going to consider. So E1 equal to E2 means in the E1, in the medium 1, which two are exist? Incident and reflected. That's why EI plus ER is written in place of this E1. Similarly for E2, it will be ET only. Why? Because transmitted wave will be in the medium 2. Now, if we substitute means first consider 1, 3, 5 equations, right? Why? Because EI, ER, ET equations we are going to consider. Now, in all cases, you just substitute Z by 0. Okay. So, now in the previous equation, see here, if you substitute Z by 0, in this case, what you are going to get? EI equal to EI into e power minus j beta 1x sin theta I. This becomes 0. And consider equation number 3. Here also, if you substitute Z by 0, then ER e power minus j beta 1 x sin theta R. Similarly, if you consider equation number 5, here also, if you substitute Z by 0, then what is left out means EI e power minus j beta 1 x sin theta I plus ER e power minus j beta 1 x sin theta R equal to ET into e power minus j beta 2 x sin theta. This will obtain from the boundary conditions means tangential components of E is continuous across the interface means that interface is aligned at Z is equal to 0. Okay. Based upon that, this equation number 7 has been obtained. Okay. Now, Similarly for H components, magnetic field intensity vectors. So H1 is equal to H2. Means what is there in the medium 1? Hi plus Hr, incident as well as reflected. And in the medium 2, we have only transmitted. Then it is represented with Ht. Okay. Then again, the same formula here also we have been applied. Means if you substitute Z by 0, consider equation number 2, 4 and 6, all even equations. See, so in this again, if you substitute Z by 0, this equation Z by 0, here also Z by 0, and in the equation number 6 also, if you substitute Z by 0, then what is there? What are the equations remains? Means 1 by eta 1 minus ei cos theta I e power minus j beta 1 x sin theta I. This is completely related to ei, incident wave. Right? EI means from this HI we will be having this one. And ER cos theta R e power minus j beta 1 x sin theta R. This is from HR, and which is equal to minus 1 by eta 2 et cos theta t e power minus j beta 2 x sin theta t. This will obtain from what? Transmitted wave field strength as HT. Okay. HI plus HR is equal to HT. Okay. Now from this, now beta 1 sin theta I equal to beta 1 x sin theta R equal to beta 2 x sin theta t. Why? Because as we know that according to the boundary conditions E1t equal to E2t, then EI plus ER equal to ET. Okay. Depending upon this, we have been equated like this. Or we know that Snell's law of reflection means the angle of incidence and the angle of reflection are same. According to that, if you substitute theta I by theta R, and these two are replaced by beta 1 x sin theta I, beta 1 x sin theta I equal to beta 2 x sin theta t. And these two from E1 and this is from E2. Okay. Now from this, and according to Snell's law of reflection, that is sin theta t by sin theta I equal to beta 1 by beta 2. Right? So use those two relations to simplify the equation for transmission and the reflection coefficients. So now from that equation number 7 means at z is equal to 0 if you substitute, then EI plus ER is equal to ET, and from this one 1 by eta 1 EI minus ER into cos theta I equal to 1 by eta 2 ET cos theta t. Okay. Now separate EI and ER terms, ET terms as respective. Then from this equation number 11, if we write the equation for ET only, then EI minus ER into cos theta I by eta 1 equal to here cos theta t by eta 2 into ET is left out. Now from this, get this term, complete term into this side. Then it becomes EI minus ER into cos theta I by cos theta t equal to eta 2 by, into eta 2 by eta 1 equal to ET only. Right? So upon simplification between these two, so suppose if you observe between these two, means EI plus ER equal to ET and EI minus ER into cos theta I by cos theta t eta 2 by eta 1 equal to ET. Okay. Now from these two relations, see. Now if you equate these two equations, means if you observe RHS part of this and this, what is there in the RHS? ET and ET. If RHS parts of these two are same, means LHS parts of these two are also same. Okay. Now from that, if you compare like this, see EI plus ER equal to EI minus ER into eta 2 cos theta I by eta 1 cos theta t. Okay. Now separate EI terms and ER terms. Now cross multiplication between these two, eta 1 cos theta t EI plus eta 1 cos theta t ER equal to EI into eta 2 cos theta I minus ER into eta 2 cos theta I. Okay, we can separate incident and reflected wave field strengths. Now it becomes, see here, now ER term. So get this ER term into this side, then eta 1 into cos theta t ER plus ER into eta 2 cos theta I equal to. Now already EI into eta 2 cos theta I minus eta 1 cos theta t into EI is left out. Now from this, if we take ER as common from this relation, ER into what is there in the left? Eta 1 cos theta t plus eta 2 cos theta I equal to. And if we take here EI as common, then what is there? Then eta 2 cos theta I minus eta 1 cos theta t. Okay. Now from this relation, reflection coefficient gamma and perpendicular means for a perpendicular polarization, reflection coefficient gamma tau is given by, it is the ratio of ER to EI equal to. Take this EI into this side and this term into this side, then it becomes eta 2 cos theta I minus eta 1 cos theta t by eta 1 cos theta t plus eta 2 cos theta I. Okay, so this is the oblique incidence with a perpendicular polarization of what? Reflection coefficient. Okay, gamma t equal to ER by EI equal to, this is the relation. The same relation which we have analyzed in the case of normal incidence at a plane dielectric boundary without considering the phase angles. There gamma equal to, we have got eta 2 minus eta 1 by eta 1 plus eta 2. So the angles means we have considered here there exists some obligation. That obligation is analyzed with respect to the polarization, right? So this is the case we have analyzed in the normal incidence case, and this is for oblique incidence. Understood, I think, the difference between this normal and oblique incidences. Okay, so in the similarly, this is the reflection coefficient of the perpendicular polarization. And the similarly, if we evaluate the gamma tau, means by adding those two, by separating those two, then we are going to get this thing. Means EI plus ER equal to ET, and one more relation as EI minus ER into previously what? That is EI minus ER into cos eta 2 cos theta I by eta 1 cos theta t. Eta 2 cos theta I by eta 1 cos theta t equal to ET. Okay, by adding these two means we can separate first from this. If you simplify, EI minus ER equal to ET into, take this complete term into this side, then it becomes eta 1 cos theta t by eta 2 cos theta I. Okay, then if you compare these two, means by adding these two, EI LHS part becomes EI plus ER plus EI minus ER equal to, then ET plus ET into eta 1 cos theta t by eta 2 cos theta I. Okay, then ER gets cancelled, 2 EI equal to. Now if we take here ET, means LCM between these two, then ET as common, then it becomes eta 2 cos theta I plus eta 1 cos theta t by the denominator we have eta 2 cos theta I. Okay. Now from this, if we consider ET by EI equal to, that is nothing but tau perpendicular. Transmission coefficient of perpendicular polarization or horizontal polarization, and it is denoted with tau perpendicular equal to ET by EI equal to. Now from this we have got 2 eta 2 cos theta I by eta 2 cos theta I plus eta 1 cos theta t. Okay, the similar equation which we have evaluated in the case of normal, that is tau transmission coefficient tau equal to 2 eta 2 by eta 1 plus eta 2. Right? Where eta 1 and eta 2 are the intrinsic impedances of medium 1 and medium 2 respectively. Okay? So this is about a normal incidence and this is about oblique incidence. Okay? This is the way we have evaluated tau perpendicular and gamma perpendicular. These ratios are transmitted to the incident as well as reflected to the incident waves. Okay? And from these two relations, we can draw here 1 plus this gamma perpendicular equal to tau perpendicular. How we have evaluated? How we are going to evaluate this one? 1 plus gamma perpendicular is nothing but what? This eta 2 cos theta I minus eta 1 cos theta t by eta 2 cos theta I plus eta 1 cos theta t. Okay. Now from this, if you take LCM between these two, eta 2 cos theta I plus eta 1 cos theta t by plus eta 2 cos theta I minus eta 1 cos theta t by, in the denominator, eta 1 cos theta I plus eta 1 cos theta t. Okay. Now eta 1 cos theta t, this gets cancelled, which is equal to 2 eta 2 cos theta I by eta 2 cos theta I plus eta 1 cos theta t. Okay. This is what? Nothing but tau perpendicular. Okay. So this is the way we can simplify, or from these two relations, we can draw one of the assumption as 1 plus gamma perpendicular equal to tau perpendicular. Okay. So what we have learnt in this particular lecture session is, firstly, how we have considered this perpendicular polarization, means from the oblique incidence. Oblique incidence with perpendicular polarization, there the electric field intensity vector is perpendicular to the plane of incidence, and that incident wave plane is to be considered as the along with the xz plane. If you consider xz plane, the propagation direction is along the y direction. Depending upon that, we have considered three types of propagation vectors for incident, reflected and transmitted waves as separately. From the propagation vectors, we have got 6 relations: incident wave, reflected wave, transmitted wave, electric as well as magnetic field intensities. From the all 6 relations, we have got here transmission coefficient and reflection coefficient of this oblique incidence with perpendicular polarization has been obtained. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.